Here's today's paper. I'm going to make model answers or as model as I can. For this exam, it's a practical skills exam in Edexcel International A-Level for Physics. It's the Unit 6 paper. So it's the final paper the students do in the International A-Level. They do 3 units with a practical skills in year 12, and then they do 2 theory units and then a practical skills exam in year 13. So this is the Physics 2 version of the practical skills. It's 80 minutes and it's 50 marks. Okay, the first question is a student investigating the conservation of momentum using a linear air track. So I actually made this video once before. I forgot to press record, so I'm doing it again. So the air track provides a cushion of air. So it's got tiny little holes in it if you haven't seen one before, and that kind of reduces the friction between the gliders, glider A, glider B, and the track. So glider A has a card on it. The card disturbs the light gate and that records the time on the timer. It then will collide with glider B, and then they'll move towards and through light gate B. So a second timer will be activated by the second light gate automatically. Okay, from the length of the card divided by the time on the timer, you can work out the speed, and therefore you can investigate the momentum in a lab. Okay, so describe how the student would initially show that the air track is horizontal before starting his investigation. This is like a zero error check. Make sure that you don't have any other uncontrolled variables, that there isn't a slope on the desk for the air track to mess your results. Okay, so I've put in my answer, if the air track is level, the speed of the glider A on its own, so you remove glider B, when pushed, and I've stressed gently because you don't want to do anything violently, will be similar when going through each light gate. So you also, if you push it slowly, you're not going to have any air resistance. If you push it faster, air resistance could be more of a factor. So you push it through, remove glider B. When it goes through light gate A and light gate B, then it should, if you've given it a gentle push, be similar when going through each light gate, or words to that effect. That's what that means, or words to that effect. Now, there are alternative ways of putting the answer down. This is just my way of doing it. For alternative answers, check the mark scheme. Anything sensible will gain this mark. So it's like having a zero error on a meter. You would have to check it. Okay, so that's the setup. The next part of the question says the student pushed glider A. The first light gate recorded the time T1 for the card on glider A to pass through it. These are T1 times, 0.34, 0.21 and 0.28. Don't worry about the handwritten one, that's my calculation for the answer. The gliders collided and then stuck together. That's where in between the two light gates. The second light gate recorded time 2 for the card on glider A to pass through it. By then, glider A and glider B have joined together, so they go off as the double mass. Both of the gliders have exactly the same mass. So 1m, this is the time for 1m's movement. This is the time for 2m's movement. The student recorded time 1 and time 2 for 3 separate collisions. So the first light gate is the top, second light gate at the bottom. The second light gate, the time is slower because the mass is double. Yeah, the mass is single, so time should be half. If the masses of the gliders are identical, m, if the momentum is conserved, then the second time should be equal to twice the first time. Show that momentum was conserved in this investigation. So all we've got to show is that each of the second times is approximately equal to twice the time 1, which I've done. So there's 2 times 0.34 is 0.68, 2 times 0.21 is 0.42, and 2 times 0.28 is 0.56. You can see how close they are. This one's the furthest away, 3 centiseconds difference. What I then did is to compare each pair of readings to see that 2t1 is approximately equal to t2 in each case. And then I did a little bit of analysis and calculations, and you get a second mark by doing some kind of analysis. And there's different ways of doing this. I said the first pair, the difference between the average value and each of the calculated double value is only 0.01 difference, so it's only a 1.5% difference between the two values and the average of the two. I then did it for the second. It's a bigger range and it's a smaller total time. So when I did that, the difference between 2t1 and t2 is 0.015, the average of it being the value I use. That's a 3.7% difference, okay? The uncertainty each way. And the third one is very close, only 1% difference. So I said all values are within a very small range, yeah? So momentum can be considered to be conserved. That's how you get 3 marks. The next bit says a second student, another student, suggests that using a piece of card twice as long, okay, so they're stressing that it's twice as long, would improve the investigation. Assess this suggestion. In general, if the card is longer, the time to go through would be longer, okay? So you're dealing with a longer value. So just like I worked out percentage uncertainties or percentage differences here, you're dividing by a bigger number. So if the card is doubled, the times, all the times should double too, yeah? Because the card will take twice as long to go through, whether it's in the first light gate or the second. So you see, I'm stressing the fact that I know they're talking twice as long, so it's a double effect. Then the resolution of the timer is still the same. The resolution of the timer hasn't changed, but the uncertainty percentage-wise will halve because you've increased the denominator and the resolution or the uncertainty, the real uncertainty, has not really changed. So that's how you get 3 marks. So I've underlined the fact that I'm doing it numerically, not generally. Anytime you're specific, you get the marks. If you're too general, you will miss out on some of the marks. Okay? It's just common sense, this paper, as long as you've covered all the skills that you need for practicals. Okay, the next question is to do with alpha particles. A student wrote the following plan to investigate the distance traveled by alpha particles in air. Okay, so as you know, alpha particles can go through a few centimeters in air before they lose all their energy and get lose it, presumably ionizing the air particles in the air. So they've written this: place the Geiger-Müller tube in front of the source. Okay, measure the distance d from the source to the tube, and measure the count, and change d and take more readings. So this is a very general plan. They want you to devise a more detailed plan to get more marks. Say if you get planning this is a 6-mark question, and I haven't written anything down. So what's missing from this plan? Well, the mark scheme gives you a list of things that you would probably agree with when you look at them. Okay, so here's the list that you can have. There are 8 things listed, and we just go through them. Measure the background count, and they don't put measure the background count, they've put measure the count rate, because whenever you're doing it, you need to specify the time that you're taking the count for. So then it is a specific number of activity of the source is always per second or per minute or whatever you want it to be. And it says ensure that source and detector are in line. Yeah. So in many schools they have a apparatus to do this, where you actually put in your source. These are closed sources, so they only let the radiation come out of the front, so these closed sources. So usually you can put them in a holder which is automatically aligned with the Geiger-Müller tube, which has also got a position on a track. So that would enable you to do that. But I think it's a key point, it's a detail point, that you need to make sure that it's not missing the detector, it's not going off at an angle. And then use a meter ruler to measure the D. So you measure the distance with a meter ruler to the nearest millimeter, yes. Measure the count rate several times, yeah, and calculate a mean or measure the count rate over a long period, a longer time. That will get your data to be more reliable and more accurate. Okay, so I always say that you have to have a minimum of 3 pieces of data so you can get a range of your data, and from that you can estimate the uncertainty or the reliability of the measurements. So minimum 3, maybe they've said several, so several to me means 4 or 5, and that allows you to estimate the uncertainty in your data. Then it says you have to subtract the background count rate from your reading, because that's what you took the background count rate in the first place. Repeat for different values of D up to 50 millimeters, because remember, alpha particles can go through a few centimeters in air. Or it says repeat until the count rate reaches what you measure to be the background count. Then you know there's no more alpha particles that are the cause of the extra count rate. It then suggests plotting a graph of the corrected count rate against the distance, so which is not a bad idea. And then sensible comment on safety to do with using radioactive sources. Keep your distance, shielding it, and never pointing it towards people. So A-level students are allowed to use closed sources under the guidance of the teacher, but under 16 they're not allowed to. So teachers normally explain all the safety concerns with using sources. So I hope that makes sense to you. Question 2 is then done. It's only a 6 marker. Okay. So the next question is question 3, which is an oscillations question using a magnet suspended from a wooden retort stand. I've stressed the word wooden, as shown. Okay, so what would happen if the retort stand was metal? Think about that while we go through the question. The magnet lined up with the magnetic field of the Earth. Okay. The magnet was given a small angular displacement, from its equilibrium position, which is presumably there, and oscillated in a horizontal plane, so it's going this way and backwards and forwards, about the string as shown. It then, so it's showing you how it's oscillating, so it's going this way and that way. Describe how the time period of these oscillations, just got to get to the question. It says describe how the time period of these oscillations should be measured to make the readings as accurately as possible. So it's exactly the same skill again. So I always tell students when you're doing oscillations, time 20 oscillations, then divide by 20 to get the period. Okay? Why do I use 20? Because human reaction timing, you're presumably going to do this with a stopwatch, is about 0.20 seconds is human reaction timing. So if you divide the time for 20 by 20, then you can divide your human reaction timing by 0.20 by 20 as well. So that gives you an uncertainty of human reaction time as plus or minus 0.01 seconds, which is normally the resolution of the stopwatches or the timers that are given in labs. And then it says repeat, calculate the mean, minimum 3 sets is best for the same reason I told you, so you can check the reliability of the data and get another way of ascertaining from the range of data. You can get from the range, you can get to the actual uncertainty, as half the range is normally the uncertainty that you're expected to know. And then it says use a timing reference. Okay, I don't tend to do that, but I know it's a good idea, so they're suggesting that you do it at the center of the oscillation. I personally find it easier to time from the amplitude, because that's when it stops moving. So like it goes this way, then this way, and back again. So a complete oscillation is there and back. Okay, so as long as you've got a reference point, you could get students to do it in pairs. I like pair work with these kind of experiments. As long as you're saying that you're using a timing reference marker, it could be something that you always pull the magnet to ensure you have a constant controlled amplitude of oscillations. And then it says you can also start the timer after the oscillations have started. You don't have to start the oscillations while you're starting the stopwatch. So you can start them going. They'll probably go quite a while, depending on the nature of the oscillating object. And then you can just get you're ready to time it when it's gone to the side where you want to start from. Okay, so that's 4 ways of getting 3 marks. So any of those points will get you the 3 marks. That's the first part of question 3. Then the real experiment starts. It then says a loop of wire, shown here, was placed vertically around the center of the oscillating magnet as shown. So when it's in equilibrium position, the field lines are going through the loop of wire. So it's a conductor in a magnetic field. When the switch was closed, okay, you've got a current going through the loop. So you've got now two magnetic fields, the magnetic field of the wire, the loop, and you've got the magnetic field of the bar magnet as well. They will interact. When the switch was closed, there was a current I in the loop of wire, and the time period of the oscillation decreased. So this is what they noticed. Okay, a student predicted the relationship will be as follows between T and I. The current changes, so you can vary the current. That's what they want you to investigate. The student predicts it will be T equals I in some form, I to the power of n, where n is a constant. Okay, so they want you to show that you can analyze anything graphically in these practical units. Okay, so it says, let's just show the question one at a time. Okay, state an additional component required in the circuit that will allow this relationship to be investigated. So obviously the two variables, the current and the period, because n is a constant, those are the only two. So if it's not a variable power supply with its own ability to change the voltage and thereby change the current, normally you would use a variable resistor. So that's what they want you to put, use a variable resistor to vary the current, yeah, and then measure T. So the independent variable will be current, and the dependent variable will be the period that is found by counting 20 oscillations or whatever method you want to use. Okay. It then says, explain why plotting a graph of log T against log I would test the validity of the relationship. So these are log 10s, so log to the base 10. So if you take log of T, yeah, going back to the equation, log of T will be equal to n times the log of I. If you don't know how to do that, you need to go and check with your maths department and make sure you know how to take logs. So this is log to the base 10. This would be in the form of y equals mx plus c, where you put log y, you put log t on the y-axis, m would then be the gradient, and on the x-axis you would put the log of I. And here there is no plus c, so there it should go through the origin. And so if you plot log t against log I, you would get a straight line graph, yeah. So it would be you have to say that this is in the y equals mx plus c. So one for saying this in the y, it's in that form. And then if you tell them what you're going to plot, so you're going to plot this on the y-axis, this on the x-axis, then the gradient would be n, and it should go through the origin if the student's relationship is correct. Okay, that's the next part. They give you some data. Okay, so the data given is, here's the different currents the student used from 1.2 amps all the way to 2.2. So this is the independent variable. I always tell my students to put the independent variable first. So I would have put it this way, but anyway, it's fine. You'll notice that all their values are consistent, so there's nothing to criticize in terms of the number of decimal places that they quoted. Okay, they've got 2 or 3 figures here, 3 decimal places here, 2 decimal places there, and so on. 3 significant figures, 3 significant figures. So that's the analysis of the accuracy of the data that you're starting with. You then need to take log of I and log of T. So that's just, I made a mistake at first. I was actually copying the log values from the examiners, their data. So I didn't realize that they then changed the order from T to T then I to I then T. So that confused me at first until I realized what they were doing. Okay, plot a graph, it says, so you get your data. You need to take log values because you want to check the student's equation works. And then you plot a graph of log t. Yeah, so when they say plot a graph of log t against log I, it means this is on the y-axis and this is on the x-axis. So even if you didn't get the previous bit, they tell you what to plot and they're giving you the grid. So you get 2 marks for working out the logs to 2 or 3 decimal places. I would use 3. Okay, well they've used 3. I don't know if they could plot that accurately or not. I actually didn't do the plot, but I'll show you their plot, the examiner's plot. you need to choose a sensible scale for both the x and the y-axis. You need to obviously label the axes correctly, so I'll show you what we mean by that. It should show log I in amps. The I and the amps goes in brackets when you do logs. Likewise, log of t in seconds. Okay, it shows that you're logging the value of time that was already in seconds. Okay, that's how you do the bracketed form of log graphs. It's the same with natural logarithms. Okay, that's something you need to make sure you realize before you come to the final exams. Okay, so the scale, accurate plotting, that they can't find that you're more than 1 millimeter away in your plots. They will check it, yeah, that you've done it accurately in the real exam. So be careful when you're plotting. It then says use your graph to determine a value for n. Well, the n, these are how you get the marks. The gradient values that you've shown clearly on your graph. So the gradient values, you should show the triangle that you've used. And I'll show you their results in a minute to show that how you did the delta y against the delta x. The correct calculation, I always tell my students, do it on the graph using as large a triangle, right, obviously shown clearly on the graph with the data. And then the value they're saying should be between minus 0.49 and minus 0.53. It's important that you've given it to 2 or 3 significant figures, because that's what we've been talking about. So you shouldn't give it to more than 3 significant figures. You must show that it's negative, and there is no unit here. Okay, you do not need to have a unit for this because they're logs. Okay, so when you are plotting your graph, bear in mind what I said the 6 marks are for. So the log to t would be there, but if you noticed all the values, so that's how you label the axes, and then the other one, the other label should be at the top, because you'll notice that we're in a negative quadrant. So this would be log of I in amps. So you'd basically make the axes there, because log t, they're all, because t is less than 1, all the logs to base 10 will all be negative. Okay, so this will be a 0 at the top, and then negative values going down to the maximum negative value of 0.227. Okay, so this goes along that side of the axis, and then the time, the current rather, will be from 0 at the top to the 3, 4, 2 you need to get. So 1, 2, 3, 4, 5, 6, 7, 8. So you have to choose the sensible scale. So you've got 8 big squares, 4.34. So 8 times 4. So you can't go in 0.4s. So 0.5s or something like that. You need to have a sensible scale. Okay. Okay, now I'm going to show you their graph, so you can see how they did it. This is the log graph that they did. There's the data at the top, and there is their graph. I hope you can read it. It's a bit dark, the photocopy that's come out. So you see here, they've got the log of current here, and they've gone up from 0, 0.5, 1.0, so we use 0.05, and they went up to 0.35, which the final value was 0.34. So they didn't need the 8th square, so they've used 7, and that gives them more space along the side to write in their figures of the log t, which goes all the way to minus 0.227. So they've gone up to 0.24, 1, 2, 3, 4, 5, 6, 7, 8, 9, and there's 3 more below that, so there's 12 points going downwards. So they've gone up to 0.24, which covers the point, the highest log value that they got in the negative sense. Okay, so that's the scale they use. They get a mark for their sensible scale. Yeah, they got a mark for their sensible scales. Both scales are sensible. They've labeled both axes correctly, and the line of best fit has been drawn, and we're assuming they have plotted accurately. So It's not my job to check the examiners whether they've done it accurately or not. And then you can see that they're going to show you how to done the calculation on that for the so 2 marks you've automatically got from up here by taking logs. The other 4 marks are from the graph. So what they've then done is they've worked out the steepness of the curve. You can see that it's negative. They've used one value here, and they put that be 0.50. The second value they've used is here. Okay, so they haven't used the whole triangle, but they've used the value there and here. So they've taken the delta y values, 0.20, the negative, they've put the negative in, minus another negative value of 0.0, can't really read that, but it's whatever it says here, 0.88 I think it is. Okay, anyway, I think the calculation is shown more clearly because they typed it up. And then the other one, so the delta, the x value is 0.5 minus 0.075. So let's just have a look at that. 0.5, and the other corresponding point was 0.075. So they've taken those two values, they've shown all the values, including the dotted lines. Yeah, make sure you're using your ruler. Make sure your presentation is good. It does get you extra marks because the examiners do not like looking at messy work. Okay, and they've given the answer to minus 0.498, 3 decimal places. And I'll just have a look at how they set it out on the mark scheme. There it is. So it's 0.2. Yes, it was minus 0.088. So I did read it correctly. And then you've shown that the bottom number is a positive number. Yeah. And it comes out to minus 0.498. Just leave that there so you can see the rest of the points that they've got for the correct calculation of the gradient. Large triangle was shown. Their value, final value, is between the negative values of 0.49 and 0.53. Okay, so they must have looked at a range of different graphs and seen that that is the accurate answers will be acceptable there. And it says 2 to 3 significant figures, negative value, no unit. Okay, that's how you get it. Okay, so that's a useful graphing skills, log graphs. They've actually given a second graph because I think some student didn't read the question and they use natural logs, which will still give you a straight line graph with a negative gradient. So they've done an alternative graph as well in the mark scheme if you care to take a look at it. Well, obviously it wasn't a straight line going through the origin as initially the student had predicted. So it says, after plotting the graph, the student modified his prediction. He suggested that the relationship between t and I should now be t equals another constant, k, I to the power of n. So he just added it in. Justify his suggestion. Well, the original graph shows a non-zero intercept, so he does need to add something in because the graph without the k in there, it has a c would be equal to 0 in the y equals mx plus c. And this is not a 0 term from the data we've been given, so you need to mention that. So this is what we showed. So he's now come up with a new suggestion. So if you take logs of this, it will be log t equals n times log I, just the same as before, but then you add the log of k to it in terms of how you take logs. Okay? So you get 1 mark for showing this, 1 mark for showing that you need to have a c-intercept or on the y-axis. So this time this will give you a y-intercept, and then the value of k from the plotted graph doesn't equal 1, yes, which we don't want it to, because if it was 1 on the log graph, it means the power k would be 0, yeah? So log of, if the value of log k was that, because 10 to the power of 0 is equal to 1. So you say, or you can write it this way, value of c is not equal to 0. That's what you want. So basically, I think this is an easier way of doing it. So the value of c is not equal to 0, so the predicted relationship is now correct. Okay? So that is the end of question 3. Question 4, the final question, is about density and measurements. So the diagram shows a 100 gram slotted mass. So this is called a slot, approximately drawn to size, to scale. A student determined the density of this metal from which this slotted mass was made. So you work out the density and then you come up with a conclusion. So state the most appropriate measuring instrument for the student to use to measure A and B. Okay, a digital caliper is ideal because first of all you can get rid of the zero error if there has any just by pressing a button. So or you can use a vernier caliper. A digital caliper is plus or minus 0.01 millimeters, whereas a vernier scale, the old-fashioned ones, are only plus or minus 0.1 millimeter. So that changes the resolution. So I think most people will go to digital from now on. And I think caliper is 1L. I often get that wrong. Okay. It then says, explain a technique she could use when measuring A and B. Yeah? So, check for zero error, it says, to eliminate any systematic error. So they want you to know about systematic errors, and they want you to know about random errors. How do you reduce random errors? Repeat at different places, calculate a mean to just reduce the chance that you've made an error either way in your measurement. Okay. So again, we keep saying that, take multiple readings and use a mean. It then wants you to calculate the area of the slot, which is the cutout part here. Yeah? So the width is A and the length is B. And it says assume the slot is rectangular. So we're ignoring the fact that there's a bit of metal left in there. Okay? The A is 0.47. They're given the uncertainty, the real uncertainty, as 0.01 centimeter. Okay? So that would be the value here. So they're given an uncertainty of 0.1. And then B, they've given to 0.005 centimeter uncertainty. Okay, well, obviously the area of that rectangle would just be the mean A multiplied by the mean B. And the uncertainty, which they want you to work out as well, is going to be the percentage uncertainty of A plus the percentage uncertainty of B. So whenever you're adding uncertainties, you add percentage uncertainties. You don't add the real uncertainties when you're doing analysis. So the multiplication of the area, A times B, is 0.47 times 2.19. It comes out to 1.03. Yeah? And the percentage uncertainty of the area, 0.01 divided by 0.47. There, that's the percentage value. Then you do it for this one the same, 0.005 divided by 2.19, multiplied by 100. So it's 2.13 plus 0.23, so it's about 2.4 to the one decimal place, so approximately 2.4%. 2.4% of 1.03, which is the value we worked out there, is about 0.02, so you quote it as 1.03 plus or minus 0.02, and you have to have the same number of decimal places for quoting uncertainties. As this is a very good question for students to learn how to do uncertainties. Part B. The student made a single measurement of the diameter of the slotted mass. Yeah, so the diameter of the slotted mass means that if it's circular, it will be right across there. Okay, so you'd have to do it again at several different orientations to make sure you are at the widest part of the circle. So the diameter was measured. Single measurement diameter of 3.81 centimeters. Okay, so that's D. Calculate the shaded area of the slotted mass in centimeters squared. The shaded area is a bit in grey, so you have to take away the area that we worked out of A times B in the question before. So the area from D is pi d squared over 4, and then you take away your answer from A3, which was the area of the slot. So this is the total area. If you didn't have a slot in the slotted masses, it would be the amount of metal that was used if it was circular. So it would be pi times 3.81, that's how much metal they'd have to use, and they cut out the slot, pi 3.81 squared over 4, yeah, which is the same as pi r squared for those students who are confused about what pi d squared over 4 is. Yeah, d over 2 is r, so therefore r squared would be d over 2 squared, which is d squared over 4. That gives you a value to 3 significant figures, which is everything we're putting to 3 significant figures, 11.4 centimeters squared. And then take away the 1.03 that you worked out from before. Here, you worked out as 1.03 the area of the bit cut out from the disk, okay, the slot. So you take away 11.04, take away 1.03. Again, we're using 3 significant figures, so this means you're really only taking 1.0 away, so you're ignoring the 3, because again you want your answer to 3 significant figures. So it gives you the shaded area as 10.4 centimeters squared. Okay, guess what's coming next? Calculate the uncertainty in the value of the shaded area. Well, the real uncertainty from D is 0.0005. So it's going to be, if they told us the D is 3.81, it means it could be 3.81 up to half of the next digit above it, or it could be 3.805, etc. So the biggest uncertainty, if you're quoting that, it means you know this figure accurately enough. So the next one will be half of the next one. Okay, so that's how you get the real uncertainty. They want to see that you can figure that out. They haven't given you that this time. So the percentage uncertainty of this D is that 0.005 divided by the value given, 3.81. Multiply by 10, it gives you an uncertainty of 0.13%. So, but the percentage uncertainty of D squared will be twice the percentage uncertainty of D, so it will be 0.26%, because each D brings its own percentage into the ball game. Okay? So the real uncertainty of D squared, which is the same as the real uncertainty of pi D squared over 4, because obviously pi and 4 have no uncertainty, they're numbers. Okay? So it will still be the real uncertainty of the area will be 2.6% of the value that we had before, but this time you have to use 11.4, which was the actual value of the area corresponding to the diameter 3.81, without removing the slotted area, the area of the slot. So that will give you a 0.03 centimeters squared uncertainty. Yeah. So, and the total real uncertainty of the shaded area then is this uncertainty we just calculated, plus the uncertainty that we calculated in the first part for the cutout part of the slot, which was plus 0.02. Now, because they're both in centimeters squared, the real uncertainty can be added. Okay, so the real uncertainty is then 0.03 from this calculation, yeah, of getting the D squared, and the real uncertainty of getting the uncertainty from the cutout part of the slot. So together we got a real uncertainty of 0.05 centimeters squared, okay, because they are the same units. Okay, next thing we need to do is the student used the micrometer screw gauge to measure the thickness T of the slotted mass. Okay, she obtained the following readings: 11.39, etc. So you can see there's not a big range in them. The average is 11.37. Yes, so 2 of them are below and 2 of them above. It's right in the middle. So there aren't any anomalous terms. Sometimes they give you an anomalous term and they see how you deal with it. Okay, so there's no real anomalies there. It's just a gradual range. So the range of the data is from 11.39 to 11.35. So the range of the data is 11.39 to 11.35, 0.04. So the range is equal to 0.04 millimeters, just for later. Okay. So let's calculate the density of the metal, where density is mass over volume. The mass is given 100 grams with negligible uncertainty. Yeah, so normally, if they tell you it's 100 grams, it means it must be at least 99.5 and at the most 100.5. So you could actually work out the manufacturer's range for telling you that it's 100 grams, because they haven't told you it's 100.0 grams. So that would mean the negligible uncertainty is just because they don't want you to have another calculation to do. So you've got the 100 grams with whatever its uncertainty is, so we're ignoring the uncertainty of this. And then the volume is the area of the shaded area, which is 10.4. That's taken the cutout part out, 10.4, the area of the disk. That's with the cutout part taken off. And then multiplied by the thickness. Remember, they want it in grams per centimeter cubed, and they're giving you this in millimeters. So the trick would be that some students will forget to change the units. This must be in centimeters, and this must be in centimeters, which is what I've done there. Change it to centimeters, divide that, and you get a density of 8.47 grams per centimeter cubed. Okay, you should really write your answer in there, but as we're just going through it, it doesn't really matter. So we are now coming to the final page of the exam, and it says, yet again, calculate the percentage uncertainty of the value of P. Well, the percentage of uncertainty of value P is obviously the uncertainty of M, which we said was 0, because it says negligible, and the percentage of uncertainty of V. I haven't written this out very neatly, but that percentage of uncertainty of V comes in two parts. The percentage of uncertainty of the A, which was 0.05, that we worked out before, out of 10.4, so that gives a 0.48 percentage uncertainty of the area. The percentage of uncertainty of the thickness, is half the range. So what we said the range was 0.04, so they divided by the mean value. So the half the range is how you use the range method to work out the uncertainty of your final answer for T. So it'll be 0.02, which is half the range, divided by the mean value, which was 11.37, and it comes out to a percentage of 0.18. So you've got 0.18 from the thickness, 0.48 from the area. Together, they give you a percentage uncertainty of 0.66%. Okay, now to the conclusion. The student thinks that the slotted mass is made from brass, which he's looked up, presumably, or we're assuming that they've been given this data, or he's looked it up for himself, which has density of 8.5 grams per centimeter cubed. Well, if you remember, we got a value of 8.47 in the calculation we did earlier, and it's plus or minus 0.66% according to this. So that's ignoring the uncertainty of the manufacturer's production of the mass. So it'll be slightly more than that, actually, in reality. And so we 8.47, 0.66% of that is approximately 0.06. So that means the value, you know the density from, it must be somewhere between 8.47 minus 0.06, so 8.41, and it must be less than 8.53. Well, since the density of brass, is 8.5, the density of brass lies within our range of our uncertainty. So it could be made of brass, is my conclusion, based on the calculated uncertainty above. Okay, and that's how you get the final answers. Somewhere in there will be the 2 marks. If you want the details, you can access the mark scheme at your leisure and go through it like I did with the graph. So I hope you find that useful. So this is the beginning of getting ready for the May exams. This is the final paper. I'll be doing other papers as well, focusing mainly on units 2 and 5, but there will be some papers on unit 1 and 4 for students doing resits as well. The marks from the January modules come out next week, so we'll know better which students in our school need to repeat units 1 and units 4. Okay, well, I hope you found that useful, so please like, share, and subscribe if you want to know when the next video is uploaded. Thank you very much for watching, and please leave a comment if you noticed anything that you would like to discuss. Okay, bye for now.